हेलो गाइस, नमस्ते। मेरा नाम है करीम। मैंने आईआईटी मद्रास से केमिस्ट्री से मास्टर्स किया हूँ। टुडे आई वुड लाइक टू एक्सप्लेन electrophilic nucleophilic interactions. By using this electrophilic and nucleophilic interactions, we can explain 90% of the organic chemistry reaction. Today I would like to explain the electrophilic and nucleophilic interactions of alkene. If we consider alkene itself as a molecule, alkene has pi electron density. Because of this pi electron density, alkene can act as nucleophile. Therefore, we can add various types of electrophiles to the alkene. If we consider reaction number 1 is acid catalyzed hydrolysis. If we consider acid catalyzed hydrolysis of the alkene, this reaction can be explained by using simple electrophilic and nucleophilic interactions. If we consider simple alkene like this, if we are adding acid catalyzed H2O, first of all we have to describe what type of reagents you have and what is our substrate. Our substrate here is alkene, comes under category of nucleophile because of it has pi electron density. If we consider H plus ion, it is considered as an electrophile, and if we consider H2O, oxygen has non-bonding electrons, therefore it comes under category of nucleophile. So reactions is all about interaction between electrophile and nucleophile. Our substrate is alkene, which is considered as nucleophile. H plus is electrophile. The step 1 of this reaction is interaction between our alkene and H plus ion. As we know, electrons are transferring from high electron density to low electron density, that means nucleophile to electrophile. As a result, in this case, we are getting a carbocation as an intermediate. Once carbocation is our intermediate, we have to consider the stability of the carbocation to proceed into second step. In this case, we have two types of carbocations, carbocation 1 and carbocation 2. You can see our carbocation 1 is tertiary carbocation, whereas carbocation 2 is primary carbocation. Here our tertiary carbocation is more stable because of more hyperconjugations. You can see here we have total 9 hyperconjugations, whereas in this case we have only 1 hyperconjugation. So more hyperconjugations will stabilize carbocation, therefore carbocation 1 is more stable as compared to carbocation 2. Now we have to proceed to second step. In second step, the intermediate is interacting with our another reagent, that is H2O. So if we consider tertiary carbocation, as we know, carbocation is nothing but it contains empty p orbital. So empty p orbital is also considered as electron deficient, so comes under category of electrophile. It should interact with nucleophile. In our reagent we have nucleophile H2O. Therefore, electrons are transferring from high electron density to low electron density. That means electrons are transferring from H2O to carbocation. As a result, we are getting a intermediate product like this, protonated alcohol. Therefore, our final product will be OH and H+. So you can see we are explaining this reaction only on the basis of simple electrophilic and nucleophilic reactions. So as we know, our alkene is nucleophile and H plus is electrophile and H2O is nucleophile. Step 1 is all about transferring electrons from the nucleophile to electrophile. Who is nucleophile? Our alkene is nucleophile and H plus is considered as electrophile. Therefore, we have to transfer electrons from the nucleophile to electrophile. As a result, in step 1 we are getting a stable carbocation. So in this case, now in step 2, this carbocation itself is electrophile. The another reagent in given reaction is H2O, which is considered as nucleophile. Therefore, electrons are transferring from again nucleophile to electrophile. As a result, we are getting the final product is alcohol. Like that, we can explain the most of the alkene reactions on the basis of only electrophilic and nucleophilic interactions. If we in this case, we have our reagent is HBr and substance is again alkene. HBr can be written as H plus and Br minus. First, we have to identify what type of reagent we have. For if we consider our substrate is again alkene, comes under category of what? Nucleophile. Again we have H plus ion, comes under category of what? Electrophile. Again we have Br minus comes under category of what? Nucleophile. As we discussed in the previous question, electrons are transferring from the nucleophile to electrophile only. So in this case also, step 1 is same. Alkene is interacting with H plus ion. Why? Because alkene is considered as nucleophile and H plus ion is considered as electrophile. Therefore, we have to transfer electrons from the nucleophile to electrophile. As a result, we are getting two types of carbocations. So, carbocation 1 and carbocation 2. So, both are generally unstable carbocations, but the carbocation 1 can undergo rearrangement to form a stable carbocation like this, which is considered as methyl shift. Because of methyl shift, the carbocation 1 is stabilized. Therefore, in second step, we have to proceed with stable tertiary carbocation. So, this should be interact with nucleophile. So, in given reaction, Br minus is the only nucleophile left out. Therefore, this Br minus interacting with carbocation, as a result, we are getting a cyclic alkyl halide. Okay. So, this is our final product. So, idea is very simple. We have to identify electrophile and nucleophile. So, in this reaction, you can see H plus is considered as electrophile and Br minus is considered as nucleophile. So, electrons are transferring from nucleophile to electrophile. As a result, we are getting carbocations. The carbocation 1 can undergo methyl shift to form more stable tertiary carbocation. In second step of the reaction, the stable carbocation considers electrophile because carbocation itself is electron deficient and Br minus is considered as nucleophile. Therefore, electrons are transferring from nucleophile to electrophile. As a result, we are getting a final product, cyclic final product reaction. Okay. If we consider this example, it's typical JEE mains question in which you can see we have to identify electrophile and nucleophile and we have to transfer electrons from the nucleophile to electrophile. So in this case we have alkene which is considered as what? Very good nucleophile, and we have H plus ion which is considered as electrophile, and along with H plus ion we have CH3OH which is considered as what? Nucleophile. So we have to transfer electrons from nucleophile to electrophile. So step 1 of the reaction is very similar to previous two questions. So here we have to transfer electrons to H plus ion. So as a result, we are getting a secondary carbocation. As a result, we are getting secondary carbocation which is unstable, but this carbocation can be stabilized by using hydrogen shift. So because of hydrogen shift, this carbocation becomes now tertiary benzyl carbocation which is considered as more stable. So step 1 of the reaction is again formation of carbocation, and then which is, suppose your carbocation is stable, is absolutely fine. If it is unstable, we have to consider the rearrangement. It can be hydrogen shift or it can be methyl shift. Step 2 of the reaction, we have to consider stable intermediate, and the stable intermediate, this is our stable intermediate we are getting in the step 1. Now again we are getting carbocation which is considered as what? Electrophile, and our nucleophile in this case is CH3OH. If we consider CH3OH, oxygen contains non-bonding electron, therefore behaves like nucleophile, and a carbocation is considered as electrophile. So electrons are transferring from nucleophile to electrophile again. So as a result we are getting a simple product OCH3. This is our final product. So like that we can explain the reactions of alkenes by using different types of the reactions. Okay. If we consider this reaction, we can see alkene, again we have alkene which is considered as nucleophile, and again we have H plus which is considered as electrophile, and CH3OH which is considered as again nucleophile. So interaction between step 1 is all about formation of carbocation. Step 1 is all about formation of carbocation and H plus. So H plus is considered as electrophile and double bond is considered as nucleophile. So electrons are transferring from H plus, that means electrons are transferring from alkene to H plus. As a result, you are getting two types of carbocations. One is carbocation 1 and which is next to oxygen atom. The other one is carbocation 2. So in carbocation 1, you can see this carbocation 1 is stabilized by non-bonding electrons of the oxygen. As a result, you will get complete octet of this carbocation. Therefore, this carbocation 1 is more stable because of plus sum effect of oxygen. Whereas in case of carbocations 2, there is no such effect. Therefore, step 2 of the reaction will be proceeded by using stable intermediate carbocation 1. So again carbocation 1 is considered as electrophile and CH3OH is considered as nucleophile. We are transferring electrons from nucleophile to electrophile. Therefore, we are getting CH3, OCH3. Like this we are going to get. So like this we can explain most of the reactions in organic chemistry only on the basis of electrophilic and nucleophilic interaction. The second type of electrophilic nucleophilic interactions in the chapter is reaction with halogen, especially with bromine and chlorine. If we consider bromine and chlorine, they comes under category of electrophiles with lone pair. First of all, we should know why bromine is considered as electrophiles with lone pair. If we consider bromine itself, bromine has each bromine has 3 pairs of non-bonding electrons. Because of this non-bonding electron represents this sigma bond of this Br2, sigma bond of Br2 is weak. Because of weak sigma bond, the sigma star has low energy. Sigma star has low energy. So according to MOT, we can say that the sigma star is available to accept electrons from the nucleophile. If we add this electrophile to simple alkene like this, Br2 in presence of CCl4. So as we know, Br2 is considered as electrophile with lone pair, is likely to form a 3-membered intermediate. I would like to explain how this 3-member ring can be achieved. If we consider Br2 here, Br and Br, here we have non-bonding electrons and we have sigma star which has low energy. If you're transferring electrons from nucleophile, why? Because your alkene is considered as nucleophile and sigma star is considered as electrophile. If you are transferring electrons from nucleophile to electrophile, the sigma bond will dissociate. Since you are donating electrons into sigma star, the sigma bond will dissociate. At the same point of time, these non-bonding electrons will be donated electrons to this carbon. As a result, we are getting a 3-membered cyclic intermediate. 3-membered cyclic intermediate. Along with this one, we are going to get a Br minus. Now, Br minus itself is considered as nucleophile, and you can see this carbon and bromine bond is very weak because of first reason is here we have angle strain. The second reason is bromine itself is electronegative. Bromine with positive charge will pull electron density towards bromine. As a result, here we have again sigma star of CBr. If you are donating electrons into sigma star of CBr, the sigma CBr bond will break. So as a result, we are going to get Br and here also we are going to get Br. So you can see again we are explaining things simply on the basis of electrophilic and nucleophilic interaction. The first point we have to consider here is Br2 itself is electrophile and considered as electrophile with lone pair. Because of this lone pair only, we are forming a 3-membered cyclic intermediate. The second, if we consider this reaction, the solvent effect is very important. If we consider carbon tetrachloride CCl4, which is considered as non-nucleophilic solvent. But if we consider H2O oxygen itself contains non-bonding electrons. Therefore, here solvent is nucleophilic. Because of this, our solvent is nucleophile, our product may be different because of electrophilic and nucleophilic interaction. I would like to explain how different products can be achieved by using electrophilic and nucleophilic reaction. If we consider again alkene, step 1 of the reaction is very simple. Alkene comes under category of nucleophile and Br2 is considered under category of electrophile with lone pair. In the previous example, in the previous reaction, we are considering H plus as electrophile without lone pair. But in this case, we are considering Br2 as electrophile with lone pair. The most important point, reason for Br2 electrophilicity is low energy of the sigma star. If you are transferring electrons into sigma star, the sigma bond will dissociate. At the same point of time, the non-bonding electrons of the oxygen donating electrons to this carbon atom. So overall, you are getting a 3-membered cyclic intermediate as our end product. So overall, you are getting a 3-membered cyclic intermediate. Along with this one, we have Br minus and H2O. Very important. H2O is also considered as nucleophile. For example, in step 2, we have 2 types of nucleophiles now. Step 2, we have 2 types of nucleophiles. Therefore, we have 2 different types of products. If we consider Br minus is our nucleophile, it can donate electrons into sigma star of CBr. If we consider H2O as our nucleophile, so we are getting different product like this. So this is our major product, this is our minor product in this reaction. So idea is very simple. Again, we can explain 2 possible products by using simple electrophilic and nucleophilic interaction. Step 1 is same because H2O is nucleophile and pi double bond is considered as also nucleophile and Br2 is considered as electrophile with lone pair. Transferring, step 1 is all about transferring electrons from the nucleophile to sigma star. As a result, we are getting 3-membered cyclic intermediate. In second step, now we have 2 types of nucleophiles. First one is Br minus, second one is H2O. If we are using Br minus as nucleophile, you will get geminal dihalide. If you are using H2O as our nucleophile, you can see electrons are transferred from H2O to this sigma star CBr. As a result, you are getting beta halo alcohol. You are getting beta halo alcohol. Very simple mechanism. All mechanisms of alkenes and alkanes can be explained on the basis upon simple electrophilic and nucleophilic interactions. Okay. So let's consider the example number 3. In this case, we are considering again we have alkene and Cl2 and CH3OH. First of all, we need to identify what type of reagents you have. First of all, if we consider Cl2, similar to bromine, that means comes under category, this also comes under category of electrophile with lone pair. Electrophile with lone pair. If we consider CH3OH, oxygen itself contains non-bonding electrons, therefore comes under category of nucleophile. If we consider this alkene, as we know, alkene contains pi electron density, therefore comes under category of nucleophile. So obviously the first interaction between step 1 is all about interaction between electrophile and nucleophile. That means our substrate will interact with one of the reagents, that is chlorine. So therefore, since chlorine comes under category of electrophile with lone pair, therefore as the initial step is all about formation of 3-membered cyclic intermediate. So as a result, you are getting a 3-membered cyclic intermediate in the first step. Step 2 is all about Now what type of step 2 is all about what type of nucleophiles we have in this reaction. You can see we have two types of nucleophiles. Type 1 nucleophile is Cl minus. If we're transferring electrons to here, you can see this bond will dissociate. And if you consider another nucleophile reagent left in the reaction is, which is known as CH3OH. If we are transferring electrons from here to here, as a result you are getting OCH3 and Cl. You can see again this reaction is also can be explained by using simply electrophilic and nucleophilic interactions. Now I would like to explain these two previous year JEE mains question on the basis upon simple electrophilic and nucleophilic interactions. If we consider reaction number 1, that is reaction number 1, first we need to identify our substrate and what type of reaction centers are there in our substrate. If we consider our substrate contains a alkene which is comes under category of nucleophile. At same point of time we can see we have oxygen which is contain non-bonding electrons, again comes under category of a nucleophile. If we consider HBr will dissociate to give H plus and Br minus, and H plus is comes under category of electrophile and Br minus is comes under category of nucleophile. So as I said, reaction is always interaction between electrophilic and nucleophilic, electrophile and nucleophile. First of all, we have two different nucleophilic centers and our reagent contains an electrophilic center. Therefore, we have to do step by step, we have to treat each nucleophilic center as individual. If we consider step 1, now in step 1 I am going to consider alkene as our nucleophilic center. So H plus we have, H plus is considered as what? H plus is considered as electrophile and alkene is considered as nucleophile. As a result, we have to transfer electrons from the nucleophile to electrophile. Therefore, we will get a simple intermediate, that is OCH2CH3, and here we have stable carbocation, and another possibility is OCH2CH3 and primary carbocation. Now we have two different carbocations. Now this carbocation one is more stable because of resonance of the benzene ring. Therefore, second step will be proceeded by using only first carbocation. If we consider first carbocation, then so we left with carbocation which is considered as itself is electrophile, and reagent left is Br minus which is considered as nucleophile. Therefore, we have to transfer electrons from the nucleophile to electrophile. So simply we will get a final product, that is OCH2CH3 and Br. As given in the question, we have to consider HBr as excess. Therefore, we have to add again H plus and Br minus. Now, we have only left with one nucleophilic center, that is oxygen, which is considered as nucleophilic center, and given reagent H plus is considered as electrophilic center. So now we have to transfer electrons from the nucleophile to electrophile. As a result, you are going to get a protonated oxygen and OCH3, and we have a Br here. Now you can see, now this sigma bond becomes weak because oxygen is protonated, oxygen itself is electronegative, oxygen with positive charge means it becomes more electronegative, means what? This bond becomes weak. As a result, the sigma star of CO bond becomes, the energy becomes low. Therefore, our nucleophile Br minus is our nucleophile. Now we have sigma star CO as our electrophilic center. Since we are donating electrons into sigma star CO, sigma CO bond will dissociate. So as a result, our final product is Simply we have OH here and benzylic bromide. Along with that one we are going to get CH3, CH2Br. Simply we explain things on the basis of simple electrophilic nucleophilic interaction. This is JEE Mains 2024 question. In this question simply we have two different types of nucleophilic center. Our reagent itself contains an electrophilic center. What is our reagent here? HBr, which gives H plus ion and Br minus ion. H plus ion is considered as electrophile and Br minus is considered as nucleophile. Here we are treating two nucleophilic centers individually. Now if we consider alkene, whenever you transfer electrons from the nucleophile to electrophile, as a result in this case we are getting carbocation as intermediate. In second case we are getting another carbocation, but first carbocation is more stable because of resonance effect. Therefore step 2 must be considered stable carbocation only. Therefore, we have to add this Br minus considered as nucleophile and carbocation itself is electrophile. Therefore, we have to transfer electrons from the Br minus to carbocation. We will get this product as a first step product. In second step, we have another nucleophilic center, that is oxygen, and we have excess of reagent. Therefore, H plus ion is H plus ion is acting as electrophile here, and oxygen is acting as nucleophile. As a result, electrons are transferring from nucleophile to electrophile. Again, we are getting protonated oxygen atom. Once oxygen is protonated, means bond becomes weak. Therefore, sigma star CO energy decrease. And therefore, our nucleophile Br minus is now capable enough to donate electrons into sigma star CO. Therefore, sigma CO bond will dissociate. This is our final product. This is very easy question. Like this, the questions like this only they can ask in the JEE Mains. Okay, if we consider second question, this is also JEE Mains 2023 question. Again, we can explain on the basis upon only electrophilic and nucleophilic interactions. If we consider second example, so step 1 of this reaction is we have an alkene and reaction with HF. So HF will give H plus ion. This H plus ion is acting as electrophile and our alkene is acting as again nucleophile. If you are transferring electrons from nucleophile to electrophile, as a result you are going to get a carbocation as a intermediate.
So now stable intermediate tertiary carbocation reacts with benzene to give aromatic electrophilic substitution reaction. Aromatic electrophilic substitution, which can be explained again on the basis of electrophilic and nucleophilic interaction. Now you can see carbocation itself is
electrophile and benzene has pi electron density, can act as nucleophile. Okay, so electrons are transferring from electrophile to nucleophile. As a result, we are getting intermediate carbocation like this. Now point is, in this case, since electrons are transferring here, you get a carbocation like this. Okay. Now very simple idea is, here we have carbocation. Now you have nucleophile F minus. Now if suppose you are adding nucleophile F minus to carbocation, you will get non-aromatic compound. See, the idea is all about to regain aromaticity. This hydrogen, this F minus will donate electrons into sigma star CH. The sigma star donate electrons into carbocation. As a result, we are getting a aromatic compound. So mechanism of this reaction can be explained by using simple electrophilic and nucleophilic interactions. Simple electrophilic and nucleophilic interaction. You can see step 1, alkene act as nucleophile, H plus is functioning as electrophile, electrons are transferring from nucleophile to electrophile. We are getting stable carbocation. Now stable carbocation acting as electrophile, benzene acting as nucleophile. We can transfer electrons from benzene to carbocation. As a result, you are getting intermediate carbocation. Now again, point is, we left with nucleophile F minus, but nucleophile F minus can donate electrons into carbocation. The product obtained is non-aromatic compound. To regain aromatic compound, we have to donate electrons into sigma star CH. As a result, we are getting aromatic product. This is our final product. Okay, so like this way we can explain all of the organic chemistry reaction on the basis of electrophilic nucleophilic reactions or acid base interactions, or we can say redox reactions. So thank you so much for the opportunity. I have beautiful approach to deal with organic chemistry. At the same time I can explain physical chemistry also. I am looking forward to working with you guys. Thank you so much for this opportunity. Thank you.